Hello friends, in this video we are going to take a look on how to increase the transconductance of a MOSFET by referring some papers and journals. First, we are going to see the paper Regrown Ohmic Contact to Gallium and Indium Arsenic Approaching the Quantum Conductivity Limit. So in this paper, their motive is to increase the transconductance of the MOSFET by using different methods. So first they created different structures of MOSFET by depositing the layers on the over the channel by using a molecular beam epitaxy. What is molecular beam epitaxy? It is a method for thin film deposition. It is widely used in semiconductors, manufacture of semiconductor device, including transistor, MOSFETs, etc. So, for this technique, we have to take this in a high vacuum or ultra vacuum place to achieve this molecular beam epitaxy technique. And they also followed regrowing the contacts between the source and the drain on a highly doped channels. So these are the parameters for this to increase the transconductance of the MOSFET. They are access resistance, channel resistivity, regrown sheet resistivity, and metal contact resistivity. The access resistance is nothing but it shows how much electrons have to overcome to flow from the source to drain in the components. And channel sheet resistivity, it is that how well the channel material conducts the electricity. And regrown sheet resistivity, so it represents the resistance of the added material that we regrown with the new material that we are added over the channel. So resistance of the added material on the top of the channel is called the growth resistivity sheet. And last one is metal contact resistivity. So it is showing the resistance between the metal and the added new material. And next, the methodology. What the methodology they use to find these electrical characteristics of this MOSFET. So first they found that the resistance is related to the number of charge carriers in the material. So which is in a quantum state. So the classical theory which is not accepted to these channel carriers. As I said, the resistivity is related to the number of charge carriers. They regrew certain materials on the channel. So they found that the total resistance became very close to the Landauer's quantum state limited conductance. So which is not affects the resistance of the MOSFET. They found that the MBE molecular beam epitaxy method, the regrown of the channel creating between the source and the drain leads to very low resistance in very low resistance in samples with high number of charge carrier. So the molecular beam epitaxy is a very useful to increase the transconductance of the MOSFET. So in this experiment, they created different structures by depositing different layers of specific material using the process MBE, molecular beam epitaxy method. So the channel material in the they made 4 different samples. They are 25 nanometer of indium gallium arsenic, followed by 100 nanometer of heavily doped indium gallium arsenic, and then 100 nanometer of heavily doped indium arsenic, and finally 15 nanometer of indium arsenic. So by the four samples, they analyzed how well the different sample conducted the electricity and how much resistance was present at various points in the electric components. So these measurements help the researchers to understand the performance of the components and to optimize their designs for the better functionality. Finally, to creating a smooth transition between the added materials and the channel material help the help to reduce the resistance and improve the performance of the electronic components. Additionally, they using one more heavily doped channel material which also leads to lower resistance and better contact with the added material. So this is the paper number 2. In this paper, their motive is to same the thing, like to increase the transconductance of the MOSFET by different method using called vertical spacer method. So the paper name is high performance raised source drain indium arsenic or indium 0.53 gallium and 0.73 arsenic channel metal oxide semiconductor field effect transistor with reduced leakage using a vertical spacer method. So in this method paper, they found that using the material indium arsenic and indium gallium arsenic with raised source drain region, and by making the indium arsenic layer thinner, they found that the leakage power of the transistor is reduced when it is not in use. So the parameters for this paper are intrinsic space, specific contact resistivity, sheet resistance for regrown source drain region. So in this paper, the material that they used indium gallium arsenic and indium rich in gallium and arsenic have small energy gaps which can cause power leakage and it affects the performance of the transistor. So to overcome this issue, they used a structure called MOSFET, so which reduce the power leakage by adjusting its drain region when the transistor is in off. However, it requires a large space between the source and the drain, so that the transistor size get bigger and reducing the density of the computer chips. So to solve this problem, they uses source drain to be positioned close to the gate, making the transistor so smaller and more efficient. But it caused some problems like leakage of power and the performance of the transistors very small. They have successfully made the transistor using the special material like indium arsenic and indium gallium arsenic with raised source and drain region. With that, they also inserted a intersonic spacer made of indium 0.53 gallium and 0.47 arsenic between the indium arsenic channel and the source drain region. So this space helps to reduce the power leakage when the transistor is not in use. So by this, the performance of the transistor get improved. So they have made two different samples, A and B. A has 8 nanometer spacer and B has 3 nanometer spacer. So by observing these two, they found that the 8 nanometer space in the sample A significantly reduced the total power leakage when the transistor is not used, and compared to the 3 nanometer space in the sample B. So by this, they said the spacer also helps to control the transistor better by making the indium arsenic layer thinner, so they further improve the transistor performance. So this results a small and more efficient transistor with better electrical characteristic which can be used in the advanced computer electronics chips.
This paper illustrates indium gallium oxide MOSFET with gate in 65 nanometer. Main idea of this paper is to incorporate indium gallium arsenide layer to create source and drain regions, which will reduce the on resistance of the MOSFET. On resistance refers to the resistance of the MOSFET at saturation region. Methodology used in this paper is molecular epitaxy. This process involves coating of target material with a crystalline substance. This process will have a huge setup with large number of effusion cells and turbo pumps. Effusion cells will effuse molecular heat into the chamber. The turbo pumps will create pressure so that the chamber will be under vacuum condition. When the molecular film is effused, it will be bombarded and the target will be coated. Parameters discussed here are high drive current and high extrinsic transconductance. This graph shows the DC output characteristics of gate length 55 nanometer device. At VGS 1.8 volts, drain current will be 2 mA per micrometer. On resistance will be 199 ohm micrometer. Extrinsic transconductance will be 1.9 millisiemens per micrometer at VDS 1 volts and VGS 0.5 volts. This paper also deals with the same indium gallium arsenide MOSFET but with gate length 65 nanometer and EOT 1.2 nanometer. EOT refers to effective oxide thickness. This also has the same methodology, that is NDE, but it also has another process called gate last process. Gate last process means from its name itself we can say that gate is lastly created, that is gate electrode of the MOSFET is finally created after the source and drain regions creation. Parameters dealt here is peak transconductance. This graph shows the subthreshold characteristics for both short channel with gate length 75 nanometer and long channel gate length 535 nanometer device. 75 nanometer gate length device shows 124 millivolt per decade minimum SS at VDS 0.1 volt. SS refers to subthreshold voltage. Subthreshold voltage means the voltage between source and gate terminal. At this voltage, the transistor starts to conduct to create a small current between drain and gate terminal. This voltage will be less than the threshold voltage. So, at this region, the transistor is considered to be in off state. So, a very small leakage current will be flowing to the channel. And 375 millivolt per volt DIBL. DIBL refers to drain induced barrier lowering. This is a phenomenon in which the threshold voltage will be decreased due to the increase in source drain voltage. Whereas a 535 nanometer gate length device shows 95 millivolt per decade minimum SS and less than 10 millivolt per decade DIBL at the same VDS.
So hello friends, I am Subhashri M. And I am here to discuss about the research paper 3-5 group compound semiconductor transistors from planar to nanowire structures. So firstly, let's see about the evolution in field effect transistor architecture and their characteristics. So coming to the figure A of this paper, this actually depicts the evolution that has taken place in the FET industry. So MOSFET, as we all know, MOSFET is nothing but metal oxide semiconductor field effect transistor. So this picture actually depicts the evolution that has taken place in the field effect transistor industry. So coming from the left to right, that is nothing but planar MOSFET to FinFET or Tri-Gate FET to the latest nanowire FET. So this actually depicts the increasing electrostatic integrity and scalability from the planar MOSFET to this nanowire FET. So this actually depicts the clear structure of the planar MOSFET, FinFET or Tri-Gate FET and the nanowire FET. So now coming to the figure B of this paper, this actually depicts the plot between the input gate voltage and the output drain current. So hearing this input gate voltage, output drain current, we all know this is nothing but the transfer characteristics of a MOSFET. So here they have mainly compared three major devices, which is nothing but the 3-5 group MOSFET, silicon MOSFET and the T-FET. So what is this 3-5 MOSFET? This 3-5 MOSFET, from the name itself you would have guessed that this 3-5 actually means the third and the fifth group of the periodic table. So some of the examples of this third group elements are gallium, aluminum and indium. And the fifth group elements are phosphorus, arsenic and antimony. So out of all the groups of the periodic table, out of the 18 groups of the periodic table, why they have specifically selected this 3,5 groups is that these 3,5 compound semiconductors have unique electronic properties that make them highly suitable for various applications, especially in high frequency and optoelectronic devices. So we have separately seen about the third group and the fifth group. So why they are calling it 3,5 compound semiconductors? It is nothing but it is actually the combination of elements from the third group and the fifth group. So some of the common examples of this 3,5 compound semiconductors include gallium arsenide, indium phosphide and gallium nitride. So coming to this slide, this figure B actually compares the three devices, 3,5 MOSFET, silicon MOSFET and the tunnel FET, which is nothing but the T-FET. So here they say that the 3,5 MOSFETs have higher mobility than silicon MOSFETs, allowing them to deliver higher currents at the same voltage, enabling them to operate at a lower supply voltage, where VDD of 3,5 is less than the VDD of silicon. VDD of 3,5 is less than the VDD of silicon to achieve the same on current. So here this is the off state and this is the on state of the device. So to understand this, simply consider a bulb. So for a bulb, if you off the bulb, the light will not glow, and if you on the bulb, the light will glow. So think of a situation where if you off the bulb and the light glows, so that is nothing but the off state current. Like if the switch is actually in off condition but the current flows, this is nothing but the off current. So here they talk about the short channel effects. This short channel effect actually in some FETs degrade the device characteristics, leading to higher off state current compared to the FETs without the short channel effects. So here the T FETs, you can see it obviously have the short channel effect, because in the off state, that is here itself, it approaches a higher current. In the lower voltage itself, it is approaching a higher current. So in the off state itself, it achieves a higher current. So this actually, it is a disadvantage. So they say that although the on current of T-FETs might be lower than the silicon and 3,5 MOSFETs, it can be achieved at a much smaller voltage. So what they say is that the on current of T-FETs might be lower than the silicon and 3,5 MOSFETs. This, as I said, this is the on state of a device, and in this on state we can see this 3,5 MOSFET has the leading current, and then it is followed by the silicon MOSFET, and then it is followed by the T-FET. So although the on current of this T-FET, the on current is, this is the on state, and the current at here, it is actually low. So although the on current of this T-FET is lower than the silicon and the 3,5 MOSFET, it can be achieved at a very smaller voltage. At the very smaller voltage itself, the high current is being achieved. So as I said, it is actually a disadvantage. So this is all about this slide. So coming to this slide, you can see this figure C. This figure C, actually it is a plot between the gate length and the V-inch. V-inch is nothing but the electron injection velocity. So here they have compared three major devices, which is nothing but the indium arsenide and indium gallium arsenide HEMTs. HEMTs are nothing but, as we know, high electron mobility transistors, and silicon MOSFETs, silicon metal oxide semiconductor field effect transistors. So the parameters here are the gate length and the V-inch, which is nothing but the electron injection velocity. So here you can clearly see that for various devices, this electron injection velocity changes with the gate length, changing gate length. So what they actually trying to say in this figure is that the electron injection velocity in indium arsenide, indium gallium arsenide high electron mobility transistors with different channel compositions and in silicon MOSFETs changes with the gate length. So as you here see that for changing gate length, the V inch changes with respect to the different devices. So the measurements were taken at specific source drain voltages where VDS is equal to 0.5 for 3 to 5 Hz and VDS is equal to 1.1 to 1.3 voltage for silicon MOSFETs. So indium gallium arsenide with different indium composition exhibits a significantly higher electron injection velocity. So what they are actually trying to say is that as the indium content increases in indium gallium arsenide, you can see a increase in V inch, which is nothing but the electron injection velocity. So they say that indium gallium arsenide with different indium compositions exhibit a significantly higher electron injection velocity compared to both strained and unstrained silicon. So as the higher electron injection velocity leads to the higher on currents in indium gallium arsenide HEMTs. So what they are actually trying to say is that as the indium content increases, it results in the increase in electron mobility. So increase in electron mobility results in increase in this V inch, which is nothing but the electron injection velocity. So you can see from this graph itself, as the indium content is low, indium 0.53, you can see the low V inch, which is nothing but the low electron injection velocity, and as the indium content increases in the indium gallium arsenide, indium 0.7, you can see the somewhat increase in V inch, which is nothing but the electron injection velocity, and then indium, for that you can see the highest V inch. So what they are trying to say is that increase in indium content in the indium gallium arsenide results in increase in electron mobility, which finally results in the increase in V inch, which is nothing but the electron injection velocity. So this is all about this paper, and thank you friends for your kind patient listening.